The last example that we have in this section is dealing with giving a recursive formula. Can you find the explicit formula? So here we've got a1 is equal to 81, and a sub n plus 1 is 1/3 a sub n. So you see over here the n plus 1 is over here. That's another way that we can write a recursive formula. So in order to figure out what this explicit formula is, or in other words, if I were to plug in 1, I get the first term, 2, I get the second term, 3, I get the third term. Let's find the first couple of terms so we know what we're looking for. Well, we know a sub 1 is going to be 81. And since this is recursive, a sub 2 is going to be 1/3 of a sub 1, or 1/3 the previous term. So a sub 2 is going to be 1/3 of 81, so a sub 2 is 27. So you know a sub 1 is 81, a sub 2 is 27. A sub 3 then is going to be 1/3 of a sub 2. Once again, taking my previous term. So a sub 3 would be 9. And then finally, a sub 4 is 1/3 of the previous term, which is a sub 3. So a4 is going to be 3, or 1/3 of 9. So the pattern that I see here is 81, 27, 9, and 3. What relationship do I see there? Well, I see that I'm dividing by 3. I'm also seeing that I'm going by powers of 3. So let's look at this from the power perspective. If this right here is 3 to the first, we know 9 is 3 squared, 27 is 3 cubed, and 81 is 3 to the fourth. How can I write that in terms of n? So if I plug in 1, I get a result of 4. If I plug in 2, I get a result of 3. If I plug in 3, I get a result of 2. And if I plug in a 4, I get a result of 1. And the answer to that is that my exponent has to be 5 minus n. So here, 5 minus 4 gives me 1. So if I plug in a 1 right here, I would get 81. 5 minus 1 is 4, which is 3 to the fourth, which I was looking for. For my second term, which needs to be 27 in the end, I needed to end up being cubed in the exponent. So if I plug in a 2 there, 5 minus 2 is 3, 3 cubed is 27. The third term needs to be a squared, so if I plug in a 3 right there, since it's the third term, 5 minus 3 is 2, which is 9 when I square the 3. So a sub n is going to equal 3 raised to the 5 minus n. So if I were to plug in 7, I would get the 7th term. The second example, a sub 1 is equal to 14, a sub n plus 1 is equal to negative 2 times a sub n. Let's figure out what that pattern is going to be. Well, first of all, a sub 1 is equal to 14. That means a sub 2 is equal to negative 2 times a sub 1. So negative 2 times 14, a sub 2 is going to be a negative 28. So 14, negative 28. A sub 3 is negative 2 times a sub 2. So a sub 3, negative 2 times negative 28 is going to be 56. And then a sub 4 is negative 2 times a sub 3. So a sub 4 is going to be negative 112. So this one we can see is a pattern of being multiplied by a negative 2. So I somehow need to communicate if I plug in a 1, I'm going to end up with 14. If I plug in a 2, I'm going to get negative 28. If I plug in a 3, I'll get a positive 56. So with this one, a sub n, we know my starting value is 14. And the way each piece changes is negative 2. So 14 times negative 2 right now, that gives me the negative 28. And I can sort of see the pattern is going to emerge. But then I need to have some exponent up here to represent every single time I multiply by the negative 2. So the way we get it so that the first term is 14, what does negative 2 have to be raised to in order to end up with just 14? And the answer is 0. This quantity has to be negative 2 raised to the 0, so it's equal to 1. So then 14 times 1 is 14. And since I need to plug in 1 for my first value, my exponent's going to be n minus 1. So there, if I plug in 1, 1 minus 1 is 0. Negative 2 to the 0 is 1. And then 14 times 1 is 14. If I plug in a 2, 2 minus 1 is negative 1. Or 2 minus 1 is 1. Negative 2 raised to the first power is negative 2. 14 times negative 2 is negative 28. And the same pattern will emerge when you go 3, 4, 5. So that will be our explicit formula given the recursive formula.